Hi, welcome to my talk. My name is Yecheng Sun. I'd like to introduce RegexScalpel, Regular Expression Denial of Service, ReDoS, Defense by Localize-and-Fix. Imagine a scenario. Here is a web application on the server side to verify whether the input email address is valid. Unfortunately, the parsing time of the regular expressions used here is superlinear for some inputs. On the client side, a normal input such as ABC at DEF-COM which can be verified by the server immediately. But for a malicious input such as yet a large number of C, it will make the server run out of a lot of resources without feedback, which is called ReDoS attack. The existing ReDoS defense strategies include regex engine substitution, input length restriction and regex repair. The weakness of regex engine substitution is omitting extended features, consuming space and bringing semantic differences or incompatibilities. The weakness of input length restriction is facing a dilemma known as Goldilocks problem, namely, the limited length is too short to accept all valid inputs or the length is too long to reject malicious inputs. Repairing vulnerable regexes can greatly mitigate their vulnerabilities. Our statistics in the table show that regex repair is the most common defense strategy adopted by developers or maintainers, accounting for as high as 92.19%. However, regex repair is challenging. The repaired regex returned by exciting techniques may be still vulnerable to ReDoS attacks and may not be semantically equivalent or similar to its original regex. To overcome these challenges, we proposed RegexScalpel, a regex ReDoS vulnerability analysis and repair framework based on Localize-and-Fix. RegexScalpel can preserve the semantics of the original regex, and the iterative repair method also keeps out vulnerabilities of the repaired regexes. RegexScalpel first leverages the fine-grained vulnerability patterns to localize the vulnerabilities and obtain the information for the repair. The information includes their vulnerable patterns, the source that is, the pathological sub-regexes, and the root causes, for example, the overlapping sub-regexes. RegexScalpel then fixes the pathological sub-regexes according to the repair patterns and the information. The repair patterns use micro-manipulations, for example, adding a lookaround, deleting a quantifier sub-regex, modifying a quantifier sub-regex, to remove the overlapping paths or reducing the maximum times of backtracking. RegexScalpel next determines whether the repaired regexes are ReDoS invulnerable and whether it can pass all the given test cases. If so, the repaired regex is called a successful one. If not, RegexScalpel continues the vulnerability analysis and repairs it. RegexScalpel finally returns a repaired regex randomly chosen from the successful ones. Next, I will introduce the fine-grained vulnerable patterns. RegexScalpel uses these vulnerable patterns to localize the vulnerabilities and obtain the information for the repair. The NQ pattern is a regex with nested quantifiers. The NQ pattern has worst-case exponential behavior when a pump string can be consumed by either an inner quantifier or an outer one. In order to facilitate fixing the pathological regex, we subdivided NQ pattern into three sub-patterns, that is, NQ1, NQ2 and NQ3, as shown in the table. The QOD pattern is a quantified disjunction whose multiple inner sub-regexes overlap. When matching a pump string, there are multiple choices among the overlapping sub-regex with worst-case exponential behavior on a mismatch. We subdivided QOD pattern into two sub-patterns, that is, QOD1 and QOD2, as shown in the table. The QOA pattern is a quantified regex containing two adjacent overlapping sub-regexes. A pump string can be consumed by either of the overlapping adjacencies. We subdivided QOA pattern into five sub-patterns, that is, QOA1 to QOA5, as shown in the table. The SLQ pattern is a regex starting with a sub-regex with a large quantifier. The SLQ pattern may cause the regex engine to keep moving the matching regex across the malicious string that does not have a match for the regex, leading to worst-case polynomial behavior. We subdivided SLQ pattern into five sub-patterns, that is, SLQ1 to SLQ5, as shown in the table. Next, I will introduce the repair patterns. RegexScalpel uses these repair patterns and vulnerability information to repair pathological sub-regexes. The NQ pattern has a redundant quantifier by nature. So to fix NQ pattern, we can remove the redundant quantifier as shown in the table. The QOD pattern has multiple matching paths across the overlapping disjunctions for a string. We need to ensure that there is a unique matching path for each string. For that, we propose three strategies, namely deleting one overlapping disjunction, adding a lookaround constraint to one overlapping disjunction, and modifying one overlapping disjunction by subtracting the first set of the other one. The QOA pattern contains the corresponding two overlapping adjacencies. We need to ensure that only one overlapping adjacency would be selected when matching on a string. We propose three repair strategies, that is, merging the overlapping adjacencies, adding a lookaround constraint to one overlapping adjacency, and modifying one overlapping adjacency. The SLQ1 and SLQ2 patterns contain the sub-regex starting with a large quantifier. The SLQ3, SLQ4 and SLQ5 patterns contain the overlapping sub-regexes. The SLQ pattern makes the regex engine slide continuously to determine the starting position of the match. So to fix SLQ pattern, we need to eliminate or alleviate continuous sliding. For that, we proposed four strategies, namely adding a start-of-line anchor to the pathological regex, replacing the large quantifier in the pathological regex with a small one, adding a lookaround constraint to one overlapping sub-regex, and modifying one overlapping sub-regex by subtracting the first set of the other one. Take the ReDoS vulnerable regex as an example. The npm package Node.js.tmpl used this regex, which aims to match the simple string formatting using the left and right brace. As shown in the phase 1, the analyzer identified that the pathological sub-regex in the box is a possible vulnerability due to its two components R1 and R2 overlap. The analyzer returned a triple, namely the vulnerability information. In the phase 2, the repair used four repair patterns to fix the vulnerability. And then the verifier checked whether the repaired regexes are successful. As demonstrated in the phase 3, except for the first one, others are successful. We randomly selected the fourth regex to report to the maintainers, and the maintainers confirmed it and released Node.js TMPL 1.0.5 with the fix. Our evaluation was conducted on the ReDoS vulnerable regexes collected from two widely used sources, the Solidal benchmark and real-world common vulnerabilities and exposures, namely CVEs. Solidal benchmark contains 34 ReDoS vulnerable regexes and npm modules found by the software lab at TU Darmstadt. CVE benchmark contains 414 ReDoS vulnerable regexes extracted from 70 ReDoS-related CVEs in recent 3 years, where collected vulnerabilities without clear descriptions, live links, or test cases were discarded. For comparison tools, we selected three state-of-the-art tools belonging to three paradigms, that is, regex engine substitution, RE2, input length restriction, LLI, and regex repair, flash regex. We consider a defense is successful if it passes all the given test cases and is free from ReDoS attack. The success defense rate is calculated by dividing the number of successful defenses by the total number of vulnerable regexes under defense. We evaluated the effectiveness of RegexScalpel on 448 ReDoS vulnerable regexes comparing with different defense tools. The table shows the number and ratio of regexes that have been defended successfully. We can learn that RegexScalpel can effectively defend 98.88% of vulnerable regexes, while the best exciting work can only defend 21.20% of vulnerable regexes. Apart from the automatic defense tools shown above, we compared the repairs made by RegexScalpel with the defending actions taken by the project maintainers. We can learn from the table that among the repaired vulnerable regexes handcrafted by the maintainers, only 77.23% are ReDoS free. RegexScalpel outperforms manual fixing and successfully repairs 99.03% of regexes. We explored whether RegexScalpel can detect new ReDoS vulnerabilities in popular real-world projects and synthesize useful repairs to project maintainers. As shown in the table, RegexScalpel detected and repaired 16 new ReDoS regexes in 10 popular projects. All the 16 repairs were accepted by the maintainers and merged into subsequent project releases, resulting in 8 confirmed CVEs. Furthermore, we calculated the semantic similarities between the repaired regexes and the original ones. To measure the semantic similarity, we tried to use the first equation. But the languages can be infinite, so we adopted the second equation. We can learn from the figure that for the benchmarks most similarities go beyond 98%. On average, the semantic similarity is 99.57%. This means that the semantics of regexes are well preserved after the repair. In summary, we proposed RegexScalpel, which can defend ReDoS attacks by automatically localizing and repairing vulnerable regexes. The evaluation exhibits the remarkable effectiveness of RegexScalpel. It achieves 98.88% successful repair ratio compared with 21.20% achieved by the best existing work. RegexScalpel helped to repair 16 ReDoS vulnerabilities in the 10 real-world projects and got confirmed by the maintainers, resulting in 8 confirmed CVEs. Furthermore, RegexScalpel can synthesize repaired regexes, preserving the semantics of the original ones and keeping the semantics as close as possible to the original ones. Thank you for your attention. I would be happy to answer any questions.